Welcome everybody to this new experience where we have our meeting through Teams instead of Zoom. So it's all a bit some issues maybe here and there. Please forgive us if it doesn't come through, and please give your feedback through the chat. Today we have the pleasure of having Junran Lee, everybody knows him as Jimmy Lee, who will talk about dust in Asia in the 21st century. This is a continuation of our spring edition of the 2026 ISAR Virtuaeolian seminar series, and the organizers Andrew, Maddie, Philippe and me. Unfortunately, I'm the only one of those four present today because they all are committed to field work and other travels. But together together with the ISAR board, we are excited to continue this series with Jimmy today. Before I introduce Jimmy, I would like to tell you the structure of today's seminar. Please keep your microphone muted unless called in in the Q&A session later. But if you have questions, please feel free to type them in the chat at any time, and then we'll read them aloud at the end of the talk, or maybe you can turn on your microphone then and ask the question yourself. The meeting is being recorded and will be shared later with the ISAR community, because there's always some part of the community that's sleeping right now. That's a thing with the global community. And please hang on with us until the end for some more updates and news. And we ask everybody to contribute to creating and maintaining a welcoming and respectful working environment that fosters diversity, inclusions, and belonging. So please welcome Jimmy Lee, who earned his PhD in environmental sciences from the University of Virginia in the USA, under the supervision of Professor Greg Okin. Jimmy then pursued his academic career with the postdoctoral positions at both Cornell University and in the Department of Geography at UCLA. In 2013, he then joined the University of Tulsa in Oklahoma as an assistant professor, where he got tenure in 2019 and was promoted to associate professor. But then in 2022, he returned to Asia and joined the Department of Geography at the University of Hong Kong, where he is now an associate professor. Jimmy has been an enthusiastic participant of many ICAR meetings and served no less than 10 years on the board of the journal Aeolian Research as an associate editor, and he describes himself as an eco-geomorphologist focusing on dust and aeolian processes and their effects on ecosystem change and human health. He was among the first to propose mechanisms by which aeolian processes, fire disturbance and grazing influence the dynamics and succession of dryland grasslands ecosystems in the southwestern USA. And he has led multiple research projects funded by agencies such as the US Department of Transportation, the NSF and NASA. Jimmy has already published more than 100 papers and in leading international journals, and which were cited more than 4,500 times. So well cited and well established scientists. This is a particular special occasion because Jimmy was awarded the 2026 ISAR Mid-Career Award, and his supporters Jeff Lee, Tom Gill and Greg Okin wrote, amongst others, "Jimmy is an encouraging, easy and exciting collaborator, confident and easy to follow project leader, and not the least genuinely pleasant human being. We all want to marry him." His leadership and insight have put on the map two increasingly important areas of aeolian research, namely the effects and impacts of aeolian processes and transportation casualties and road safety, and the intersection of aeolian processes, soil biochemistry and dryland plant ecology. So we are quite excited to have Jimmy as a speaker, and we'd like to welcome you all. And with that, I give the floor to you, Jimmy. Please start your talk. We look forward to it.
Thank you so much. Thank you so much, JB. I really appreciate it. It's been quite a long process to make this happen. I really appreciate all these efforts in the past a few months. And good morning to the colleagues in Europe, and good morning, good afternoon for colleagues here in Asia. And I know colleagues in North America are in sleep, most likely. Yeah, this is my first time to attend this ISAR virtual seminar, and we use the Microsoft Teams software, and it turned out it worked really well at this moment. I also want to mention that JB planned this event so carefully and so well, and he basically we log into this system like 20 minutes ahead and get everything right and test everything. It's so impressive. As I mentioned to JB that I was in this similar some kind of similar virtual seminar, Diana, in North America, and we just run really loose everything. Just we just didn't run this. Um, well prepared. We are carefully planned seminar series. Anyway, um, again, thanks JB for the introduction of my research, my academic career. As many of you may know, I work in the U.S. for a number of years, and then a few years ago, I choose to come to Hong Kong at University of Hong Kong geography. And as a result, I sort of have to switch my research topic from North America mostly to here in Asia. And I'm going to share with you today is our efforts to do some DOS research in East Asia in particular, and in the 21st century, primarily from 2000, early 2000 to pretty much currently. All right. So just refresh your guys' memory if you are not familiar with the geography here in China and Mongolia, that part of East Asia. And basically, a large part of East Asia, particularly China and Mongolia, are drylands. They are many of them are arid and semi-arid. As you can tell, they are primarily located in northern and western part of China and large part of Mongolia, and with large area with large population. Of course, if you consider the population in China, this arid semi-arid lands support over 280 million people here in China and nearly 3 million people in Mongolia. And in terms of geomorphology, in terms of soil, this arid and semi-arid areas that are potentially the sources of dust emission are generally sandy, right? Some of them are mobile, some of them are sandy field. And they are widespread in Mongolia and northern and western China. And many of you guys probably heard that many dust emission source areas, including East Asia, have declined dust emission in the past number of decades. And this has been confirmed by a lot of ground records. Here, for example, in China, these records are primarily from northern China. We have the records from 1950s to pretty much today. And this is in terms of severe dust storms per number of severe dust storms per day in the records in China. And as you can tell, the average number of severe dust storms in China is almost 4 times a year over this from 1950s to today. And there's a strong declining trend in terms of that particular dust event. And I have to tell that similar long-term records is almost non-existent in Mongolia. So I couldn't show the records in Mongolia. And interestingly, in the past few years, particularly 4 years actually, and both China and Mongolia actually experienced very extreme, very impactful, very widespread dust events. And that is kind of counterintuitive to many people, right? Since we are experiencing a very strong declining trend of dust activities, how could we end up with very impactful, very widespread dust events in the past few years? So that actually motivated us to think about our research, what we're going to talk about in the coming slides. So for those extreme dust events that we experienced in the past few years, 2021, 2022, 2023, 2024, pretty much four years in a row in the past 5 years. And I show you some of the pictures and some of the images of this 2021 very widespread, very impactful kind of dust storm, March 13th to March 17, 2021. And what happened was there is a strong cyclone that in Mongolia and caused very strong wind, and then that wind blows toward China and further to the south part of China mainland. And the damage of that dust event was extensive, both in terms of property damage, in terms of air quality deterioration, and also in terms of life. And there are multiple casualties in Mongolia, and there's millions of cattle kind of being killed or lost or missing in Mongolia and part of Mongolia in Inner Mongolia in China. And on the right, I show you a couple of figures. Show that on the top that shows the PM10 and PM2.5 recorded in Beijing. Those are official data reported by the government. And as you can tell, the peak time of PM10, PM2.5 are hundreds of times higher than the World Health Organization recommended level, right? For example, for the PM10, WHO 24-hour guidelines is 45 microgram per cubic meter, and whereas for PM2.5, much lower, 15 microgram per cubic meter. So those numbers are, I mean, the actual PM2.5, PM10 during that event were simply just hundreds of times more than those World Health Organization guidance. And we also run some preliminary studies on the flux and emission of this dust event, and which show that the peak time of the dust are almost no same for more than 10 years in China history. And another thing that many people talk about here in China is that, well, the Chinese government have initiated multiple levels of ecosystem restoration over the past number of decades. And many people consider, because of this ecosystem restoration efforts, that lead to the reduced dust emission in China. And then all of a sudden, again, in the past few years, we experienced apparently quite a serious dust events in the past few years. And then again, it caused us to think whether those ecosystem restoration actually worked or not, or how much they work, right? Those are the questions that I also want to touch upon. Now, for the case of Mongolia, the ecosystem restoration efforts were a lot later, right? You guys probably heard about the so-called 1 billion trees national campaign in Mongolia that were launched in 2021. And they apparently learned from some of the successful stories in China, and they want to have their own kind of tree planting efforts to restore that land degradation in part of Mongolia. And also, they also hope that kind of efforts could also counteract the climate change, right? And that initiative is going to plant 1 million trees by 2030, and they also said they're going to affect 77% of Mongolia's land. And apparently that's a very ambitious effort, right? If indeed these 1 billion trees are planted and most of the trees are able to survive, which is a very big deal, and that would indeed affect the climate, affect the land degradation or ecosystem restoration in Mongolia, and hopefully it could also affect dust activities in China. And actually, the reduced dust events, reduced dust activities in East Asia has been investigated by a lot of scholars, right? And then people think about what are the reasons behind, what are the drivers behind, and he actually went beyond ecosystem restoration. Apparently, that could, right? When you have ecosystem restoration, you end up increase the surface vegetation cover. And then apparently that's going to reduce dust emission, and that could potentially reduce your dust activities in East Asia. But we actually found there are more drivers than that, right? For example, people found that surface wind speed has substantially reduced in certain part of Eastern Asia. And also there is a change in soil moisture on the surface, right? And the soil generally becomes wetter in certain part of Eastern Asia. So those factors combine together to be able to explain the reduced dust activities in East Asia. And I want to mention this particular study by Wu et al. 2022, published in NC Nature Communications, which quantify these three so-called three drivers. They argued that the decreased surface wind speed contribute to up to 46% of the dust reduction in East Asia. Increased vegetation cover, just quantified by leaf area index, contribute up to 30% of dust reduction, and increased soil moisture contribute up to 24% of dust reduction in East Asia. And we want to re-examine those numbers by using a longer data set and by using more updated data set. And later on, I'm going to show you our results as well. So basically, I just talk about what we observed, what happened. Those are really our motivations to do our research, right? We have the overall declining trend of dust activities in East Asia. However, in the past few years, we experienced a number of extreme, high impactful dust events, and in both China and Mongolia. And those kind of situations are troublesome, right? People think we did a lot and we already reduced dust activities in China, reduced dust storms in China. However, and since may not work out. So we were wondering what's the situation right now? And we sort of went beyond the already established dust reduction in East Asia and asked a number of questions, right? And for example, our first question is that where the dust come from, right? And we want to have a high resolution, both spatial and temporal distributions of dust emissions in East Asia, particularly in China and Mongolia, and how the source areas have evolved since the 21st century, from 2001 to today. How those dust areas, some of the areas may become dust areas, some of them may not become a dust area anymore, right? And second, what are the relative contributions of, I call it Chinese dust versus Mongolia dust? Basically, the dust that emitted from China versus dust emitted from Mongolia in East Asia in the past two plus decades. And I also want to share with you a couple of research that we are currently work on. And the first one is that my students currently work on an effort to sort of improve the dust emission scan that has been widely used, hopefully to improve the dust emission efforts by including the suppression effect of brown vegetation. Right? You guys probably heard the so-called brown vegetation or non-photosynthetic vegetation versus green vegetation or photosynthetic vegetation. Right? Some of the dust emission scans actually only consider green vegetation or photosynthetic vegetation. Therefore, those scans overlooked the suppression effects of brown vegetation or non-photosynthetic vegetation, which is very common in those arid and semi-arid lands. And the last question that I would like to touch upon, this is also ongoing, is that we had a meta-study, we had a meta-analysis to try to figure out from the modeling perspective whether the Earth is becoming more dusty or become less dusty, right? By basically analyze the published paper on global dust emission estimate from the earliest to today, basically from the 1980s to today. And based on that, we further want to examine the role of East Asian dust in the global dust cycle. So let's move on to the methods and data of our first question. Basically, as I said, we use a widespread Shao 2004 dust emission scan. For those of you who are familiar with Professor Shao's research, and he's very well established in terms of dust emission modeling, and he developed his fairly widely used scan, dust emission scan, and the Shao 04 emission scan was based upon his previous version of dust emission scan, which is very much based upon the principle of so-called bombardment or sandblasting will cause the emission, right? And then emission can be quantified with certain equations. And another thing that I do want to mention is that these dust emission scans, or many other dust emission scans, they are also based upon the surface vegetation, right? When you want to quantify surface vegetation, and then later on you quantify the threshold and friction velocity, and later, and of course the partitioning of momentum. And you have to use lateral cover, the term, right? And then when you use lateral cover, and many scans use leaf area index, and because lateral cover is basically impossible to measure at large scale, right? You could measure it in the field, but it's very time consuming and effort consuming. Now to quantify lateral cover, you could use leaf area index or some other empirical equations. And when you use leaf area index, you basically very much based on remote sensing, and you use remote sensing, you very much based on NDVI or the green vegetation remote sensing. Again, therefore, you actually ignore or you overlook the suppression effect of brown vegetation. And now this is a flowchart of the dust emission scan. And currently I'm logging to go to the individual equations. But a couple of things that I want to point out. Basically, the first thing is that natural cover in that scan is considered to be proportional to leaf area index, okay, LAI. And surface roughness and vegetation cover is basically quantified using the photosynthetic vegetation or green vegetation, again, by using LAI or NDVI. And therefore, this kind of mechanism typically basically overlooked or ignored the dust suppression effect of brown vegetation or non-photosynthetic vegetation. And again, we have our model inputs that I list over here. And those are fairly standard. A number of them are fairly standard model inputs in terms of land cover, soil texture, and then surface properties, moisture, velocity, and slow cover, and so on. Now, I do want to point out the leaf area index, which is a very critical parameter for the scan. And previous study used different data sets of leaf area index. The effort that we took using the most recent we call GLASS data set, version 6 GLASS data set, which fortunately actually was developed by my colleague here in the Department of Geography at the University of Hong Kong. And this data set has high resolution, has been widely verified, has been widely used, and is considered to be superior than previous version of similar data set. So we use this data set, and later on we actually yield fairly different results in terms of our eventual dust emission estimate. And for the ground data, we actually had the synoptic station data over China. Again, I want to declare that this data is very much based on the stations in China. And we have very limited stations in Mongolia, but the data is largely not available, right? And those dust events have been classified into a number of different categories: dust suppression, blowing dust storms, and severe dust storms with corresponding visibilities and wind spread. I want to make sure that those classifications are very much the Chinese system. I know North America or colleagues in Europe may use different kind of classifications in terms of the dust events. And now to deal with the fact that the SHAO-04 dust emission scan overlooked the suppression effect of brown vegetation, we developed an approach by using so-called multi-end member spectrum mixing analysis. If you do remote sensing, I'm sure you know this effort. Many of them we call spectrum mixing analysis, spectrum unmixing analysis, and so on. So that's a similar effort that we took. Basically, that MESSMA is to address surface heterogeneity and end member spectrum variability, therefore to achieve higher accuracy in fractional cover of the ground. And we had 6 end members. Many similar approach actually do not have that many. I know typically you have PV, MPV, and then bare soil, right? And we went beyond that. We have dark surveys, which could be rock, could be water, and then we have the ice and snow on the ground. And now our MASMA experiments actually include the original SHAO-04 configuration, and we also have modified configuration from B all the way to H by including different components of vegetation on the ground, PV, photosynthetic vegetation, non-photosynthetic vegetation, and then we have some other end member or some other components on the ground, BS, bare ground, DA, dark surface, and so on. And I do want to point out that we have some kind of empirical numbers that we include in terms of calculation of factor of erodible surveys to examine how this different range of the empirical numbers could modify or could change the eventual modern results of dust emission estimate. Okay, let's move on to the results. And the spectral patterns of dust emission in East Asia, we had our average emission from 2001 to 2023 that shows the hotspots of dust emission locations. Basically, many of these hotspots are located in China. Of course, we have another major spot that's going to be shared by China and Mongolia, which is the Gobi Desert. But overall, in terms of area, the source area in China is about 4.5 million square kilometers, whereas 1.4 million square kilometers in Mongolia, much less in terms of the dust emission area. And in terms of dust emission trend, which is something that we think is quite unique and important. So we have the dust emission trend from 2001 to 2023 that shows areas with significant increase, significant decrease, and non-significant increase, non-significant decrease, right? And our modeling results show that most regions, most areas display a declining trend of dust emission, which is generally aligned with ground-based records. And the non-significant increase in trends we do find some non-significant increase trend in Taklamakan Desert and parts of Gobi. And in terms of the decreasing area, the significant decrease in trend across nearly 2 million square kilometers in China, and much less in Mongolia. Even we could have the proportion, right? The total area in China is 4.5 million square kilometers, and total area in Mongolia is I believe it's 1.4 million square kilometers. But in terms of the percentage of decreasing, China is much higher than Mongolia. And the trend and the contribution of dust emission in both China and Mongolia. And now I do want to admit that when we do this modeling exercise, we actually had a hard time to accurately verify our modeling results, right? This is not just our modeling. All this large-scale modeling would have similar challenges. And what we did is that we aligned our modeling results with the ground-based observation of a number of days of dust emission. And it would be really difficult to align with the actual concentrations of ground-based observation, because again, this large-scale when you use large-scale modeling, your modeling is in terms of 10 kilometer by 10 kilometer, or even more, right? 50 by 50 kilometer, whereas your ground-based observation is just one specific location. So. And therefore we use the patterns of number of days observed by the ground-based stations versus our modeling results, and we found the mean annual frequency of dust storm closely aligned with the regions of high dust emission locations in terms of modeling. And here's particularly at the station recording over 5 dust storms days annually in springtime. And on the right is our the number of dust storm days and dust emission this should be in entire East Asia. And again, both show a fairly clear and strong declining trend, right? And the spring dust days actually had a 262 days per decade of decreasing, and similar, it was parallel to a substantial reduction of spring dust emissions in both China and Mongolia. And this is one of our sort of highlight results that I really think is important. This is in terms of dust emission and their contributions for China and Mongolia. We actually calculate this separately between China and Mongolia. And on the left is emission, on the right is there's contribution, and there's a number of components on this diagram. I want to quickly go through it, right? And you have the China emission, and you have the Mongolia emission, and then the dashed line shows the China trend and Mongolia trend, and the bars show the China contribution and the Mongolian contribution. And we originally anticipated that the contribution of dust emission from China would decrease, right? Because we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, right? And we had such a high dust emission, nationwide efforts of ecosystem restoration, which improved forest coverage, increased the quality of grassland. But it turned out that was not the case, at least from our modeling efforts from 2001 to 2023. And the contribution of dust emission to entire East Asia from China is fairly consistent, right? And overall, we have up to 69% of dust emission was contributed by China, basically. And then the rest of 31 is contributed by Mongolia. And you might argue that makes sense, right? The area of China is much bigger than Mongolia in terms of the dust emission source areas. That is true. But again, we originally anticipated, or our hypothesis was that because our ecosystem restoration effort, that percentage or that relative contribution would decrease, right? Would reduce. But we did not observe that. And then therefore we argue that there's no significant decline of Chinese dust dominance in terms of dust emission in entire East Asia. And their seasonal variations is also fairly clear and also consistent with ground-based observations. And dust emission in East Asia peaked during the springtime, March and May, for both countries, China and Mongolia. But we do notice that Mongolia actually had slightly more widespread dust emission events, right? Out of March and May, there's some other months when dust activities could still be active. And in terms of the land that generate dust, barren lands is the primary land use where dust is emitted, right? Barren land in China, barren land peaked at over 180 teragram in specific spring months. And in terms of grassland, this is kind of good news for China. And a notable decline after 2006 in terms of their sources of dust emission. And whereas in Mongolia, grassland is still high levels in recent years in terms of their dust emission contribution. And drivers of the emission of decline, as I said, there is already earlier study that show the primary drivers are wind, vegetation, and soil moisture and their relative contributions. We went ahead, used different data sets with longer periods of modeling, and we come up with some different numbers. And what we found out is that for the combination of China and Mongolia, and we actually found out that leaf area index or vegetation played the leading role with nearly 42% of contribution, and soil moisture 35%, and wind 23%. And also, those relative contribution numbers are different between Mongolia and China in terms of their relative contribution to the reduction of dust emission in East Asia. And we also examined, we modeled the three extreme dust events in the past 5 years, in 2021, 2022, and 2023. In terms of their evolution, in terms of distribution, hotspots, and overall flux, overall emission. And we come up with some numbers, right? First number would be the contribution of those extreme events to dust in East Asia. And 51 to 60% from China. Slightly below the longer term average, with 69. Okay, and in terms of the total emission, 46 teragram in 2023, which is one of the largest in 21st century that we recorded so far. And I also searched some other individual events, for example, in Australia, in Middle East or Western Asia, and this 46 teragram of total dust emission is actually quite high in terms of the overall emission of dust for one individual dust event. Okay, so let's jump to the second research question, or second research that we are working on, which is by using the MAXIMA to constrain dust emission scan and to see how the dust emission estimate is. And what this slide shows is that we use our model experiment A, which is the original SHA-04 dust emission scheme, and their associated parameters, and we compare the difference between the modified dust emission experiment or dust emission scan and the original. So we use their difference, and we end up with their anomalies, right? It's going to be more, it's going to be less, and what we found out is that experiment B is going to be positive anomaly, so it's even more than the SHA-04, and more importantly, the actual modified dust emission scan or model experiment from C to H, they have strong lactive anomalies. Basically, the reduced dust emission scan that were given by the original SHA-04 scan, and substantially reduced the amount of dust emission. And dark area, we actually use a different kind of empirical numbers to weight the dust emission, to weight the dark area, that factor, and also play important role in terms of the overall dust emission estimate. And now, without ground truth or ground validation, those modern results may not carry too much weight. We do have some ground records, luckily, and we actually, well, those ground records again are very much based upon the records in China, which I'm going to show in the coming slide. And now, again, here is our model experiment. The A is the original SHA-04, and then B all the way to H are modified, and which show the dust emission from individual countries of China and Mongolia. And as you can tell, again, even with modified dust emission scan, China still play a leading role or play a primary role in terms of overall dust emission in East Asia. Now, with the ground validation or with the ground validation, and again, we compare some of the available ground records, and by using a so-called ratio, and HD, NC, ND are just where the ground station are located in China, and the ratio, apparently ratio 1 would be kind of nearly perfect, right? If it's higher than that or it's lower than that, and I think it's reasonable, right? We are a few factors above or below, or even less than one factor below the ground observed data. Which again, if we do this kind of scale of modeling, I'm satisfied. I'm happy with the modeling results. And another way to evaluate our results is by calculating the so-called normalized mean bias, NMB, or normalized mean error. And we can, again, compare with the model experiment A, which is the original, with 72.2% of normalized mean bias or normalized mean error. And then we use our modified modeling experiment, which significantly reduces errors, right? You can tell from, particularly from C all the way to H. And so that tells us that the MAXIMA could become a potential successful modification of the original SHA-04 dust emission scheme. Now I have really a few slides to share with you a research that has been conducted by one of my undergraduate student assistant in my group. And what we did is that I asked her to do a meta-analysis by putting together all the publications from 1980s, from 1970s originally, but turns out from 1970s there was barely any global dust emission modeling publications. And then we end up from 1980s all the way to 2025. We searched all the papers published and that investigated global dust emission. And we found out the so-called the number of published data, number of published papers, and their individual peer-reviewed publication, and the scans they use, and the author's country, and we came up with these results that I want to share with everybody. And apparently, in terms of number of records, we end up with only 144 effective records, right, out of a few thousand original data, and then we later down to 144. And there is a fairly clear increased trend of these published paper that investigate the global dust emission, and particularly in the past few years. But somehow 2015 it was relatively low around that period of time. And in terms of dust emission scans, this is actually fairly interesting. I'm sure many of you guys know these models, these scans, Xander, Galox, and Verticrina. And those are the top threes in terms of dust emission scans. And I was wondering about the SAO4. For some reason, there is only one global scale studies. I can tell the SAO4 has been used for a number of regional studies, but those studies again are excluded from our meta-analysis because they do not present global data in terms of global dust emission. Now, in terms of authors, first country, and it turns out United States play a leading role with 38.2, and then France 23.6, UK, and Germany, and we add all these European countries together. There's going to be more than the United States unknown, right? And I thought China would play a fairly important role in terms of those publications. It turned out it's not, right? Only 7 or 4.6 of those publications are actually originally from China. And we have Spain and Japan and so on. Now, this is the first version of our data. It's still preliminary. We want to answer whether from the modeling perspective, the Earth is becoming more dusty or less dusty, right? Apparently, this time scale is fairly short. It's only from 1970s to today. We're not talking about the geological scale of time. Now, for that past some 5 decades, our results showed that the Earth is actually becomes more dusty. Okay, we have an increased trend of modeled estimated dust emission, right? From 480 to teragram per year to 6,000 teragrams per year. I knew there's actually some study that actually had a number actually more than 6,000, and we consider those estimates are going to be outliers, and we actually did not include those extreme estimates. We simply don't trust those numbers for some reason. And with a mean, this should be a mean MEA that I have a table over there of 2,554 teragram per year, and medium 2,158, and so on. And we have global dust emission trend. Then wait a moment. What is the so this on the right, top right, is our fine dust. Fine dust is defined to be less than 10 micrometer in terms of diameter, and also has a fairly clear increased trend of dust emission. Okay, interesting. So from this data, I show that the Earth is actually getting more dusty. And I know that's probably different from many of our knowledge, right? Because some of the published data show that North America, excuse me, East Asia has become less dusty, and I know there is a paper said Western Asia or Middle East is become less dusty, and even there is probably paper said North America has become less dusty. Okay. And how could all these dust source areas become less dusty, but the Earth, it becomes more dusty? So it's an interesting question. I want to seek you guys' advice and seek you guys' comments. And then in terms of source regions, apparently North America, North Africa and Middle East and West Asia and Australia, and these are in terms of number of records that focus on those source regions. And in terms of their relative contribution, this is also very interesting, right? We know North America play a major role. It actually contributes on average 55% of global dust. And then we have the Middle East and West Asia. Now, by the way, Middle East is actually quite a different definition. Different papers use different geographic definition for Middle East. Some part of the paper include Egypt to be part of Middle East. Some of them only consider Asian part of Middle East. So there's something about that geographic location, geographic area, and Central Asia, East Asia, in terms of percentage of overall contribution. And now East Asian dust trend, and in terms of number of publications, apparently that increased in the past few years. In terms of their actual dust emission, again, this is quite interesting as well. We expect, as I just mentioned, we expect that the East Asia is going to decrease in terms of dust emission percentage, right? Because it decreased in terms of overall emission. But we found out that fine dust, in particular, actually the relative contributions actually increased, right? In terms of their dust, emission, actually magnitude. Whereas coarse dust basically goes up to 20 micrometer decrease, indeed. Okay. And we took the logarithm of this original data. We did these two panels, these two figures again. The trend or the trends are similar, right? Increase for fine, decrease for coarse. So our take-home message, I just simply summarize what we had. Take-home message is that first message is that we have the Chinese dust dominance, okay, in both long-term average or individual extreme dust events, okay. And we have different drivers for dust reduction in China versus in Mongolia in terms of their relative percentage of moisture, leaf area index, basically that's vegetation, and wind speed decrease. And the third is that we have, at this moment, we consider our dust emission modeling improvement is going to be successful. Our paper has not published yet. And we consider that the maxima is an effective tool to modify the original style for dust emission scan, or any scan that based upon leaf area index or the lateral coverage of friction partitioning, right? And then lastly, we have the open questions of whether the Earth is getting dusty or more dusty or getting less dusty. Again, we can approach this question by using different approaches, but our efforts is by analyzing the published data or published papers. But we have to be clear that whether those published papers or published modeling results are actually reflecting the dust emission on the Earth is actually questionable, right? Because this modeling studies in different data sets, right? And they define different dust emission source area as well. Many of you guys probably know that in the past few years, we actually discovered or we actually include more source areas that were not included in previous studies. Those include like high latitude, high longitude dust emission source areas in Alaska, in Antarctic, or in high plateau areas, and or dust emissions after, for example, some fire events. Okay, and that could potentially increase the available or the actual dust emissions on Earth, right? But those actual dust emissions were not considered, were not modeled in earlier studies compared to more recent studies. So I think there's a lot of open questions for me and for you guys to consider. Again, I would seek your guys' comments, seek your guys' advice, how to sort of make this meta study more reliable, more convincing, and pretty much with that, I want to acknowledge a lot of collaborators, my funding agencies, and again, I want to thank JB and thank a lot of colleagues in ISAR for giving me this opportunity to share my research and also later on to go to Africa to meet with a lot of colleagues over there. All right, thank you very much. I'm good to answer questions or comments.
Many thanks, Jimmy, for an excellent talk. I particularly like your remark on modeling versus truth.
Thank you very much.
Wondering what truth is, but yes, please feel free to ask your questions in the chat, or if you want to raise your hand and ask your question yourself through your microphone, please don't hesitate. I've got quite a few questions myself, but I would like to give you the opportunity to shoot.
Yep.
And maybe to start the discussion, Jimmy, if I may.
Sure.
You mentioned soil moisture, but I don't think you mentioned precipitation. Do you consider precipitation at all? Because I noticed that, for example, in 2023 you had a huge event of dust outbreak, and 2023 was an exceptionally wet spring in Europe. So I wonder what's the connection there, if there's any.
Good question. I think for the individual precipitation event or rain event, and that should be incorporated into the overall change of soil moisture, and which apparently affects the threshold velocity and dust emission. And so that would be considered to be part of the soil moisture increase of dust emission drivers and dust emission reduction driver, I should say. And yeah. We did not consider individual, and then also the study that I know did not consider individual rain events, and for the overall decrease of dust emissions in East Asia.
Okay, thank you.
All right.
Frank Limko raised his hand. Frank, do you want to open your microphone and ask your question?
Yes, thank you very much for this talk, and glad to meet you in Namibia soon in July. Sure. Well, I worked in Central Asia quite a long time, and my thing, I'm a geomorphologist working in the field. I enjoy your talk very much. I have three comments or even remarks. We observed with dune movements in recent studies that precipitation enhanced and dune movement reduced. If you reduce dune movements, the sand is also a driver for the dust emission. So of course, I think, and I like your trends. So we can discuss this in Namibia. It's quite sure. The other thing is that the dust sources are the paleolakes. We have quite a lot of paleolakes levels, which are huge dust emission. Do you focus on that somehow? Because I think I observed that during dust storms, which I was in the field. That if you have a strong wind, after a few hours, sometimes 10 hours, sometimes more, especially huge dust plumes come out of the paleolakes. And of course, lake level rises a little bit since the last decades as well. So of course, this emission also getting smaller. What's your thinking about dust sources of paleo lakes.
Say that again. What lake? What the word that you you talk? I didn't catch that last word what lake?
The lakes in Central Asia, especially in Mongolia, but also in China, a lot north, for example, are much larger in the past, and they dried. And dried lake surfaces are clay-rich, and they are huge production of dust. Okay. Now the lake level rises again a little bit, so this dust resource, of course, due to wetting of the climate, getting reduced. But I saw that these are the huge dust emission spots. For example, also at the end of the Haihe River, Gashunor, Sokonor, I have been there. So these are huge dust emissions.
Excellent point. I'm so excited that you mentioned this, because I tell you, one of my students actually worked on that overall idea. Why? Here's my background, my part of background. You probably noticed that there was a 2022. There was a paper published in Science, which is by one of my colleagues, and they examined the global scale lake shrink, basically the sort of the volume of lake, the water volume lake decrease global scale. And that pointed to your question. Basically, a lot of these lakes in arid, semi-arid areas, the area have been decreased. The volume water has decreased, and which apparently exposed the lake bed to the surface, and which could become an important dust source area. And my students actually work on that thing. We actually want to quantify dust emission from these dry lakes, or from these lakes with reduced water area, or reduced water. And she's currently working on that, but apparently we want to work on the global scale. That's going to take some time. And what we did right now is that we actually work on the area sea in Central Asia right now, and which is probably by far the most typical and most large scale lake in terms of the change of water volume and the increase of dry lake bed and that kind of nature. And apparently, in terms of their dust emission, they could become very important sources of dust emission. And our study, and also the current study that I know, did not distinguish whether the emission is from this dry lake beds or from other areas. Okay, we did not separate those dust emission sources. And but we know that there's other depressions, particularly in Africa. That depression itself contributes a high percentage of dust emission in North America, but that's not considered to be a lake anymore, right? And for those lakes, I don't know what is their percentage or the role in East Asia. If you don't consider the area sea, only consider the lakes in East Asia, Mongolia and China, and they might be important. But I also want to remind you that here in China, there's a trend that many of these lakes actually become wet again. Okay, particularly in the past few years, some of the lakes some of the dry lakes actually refilled with water, at least seasonally, and that's kind of something new. And even for some lakes that were totally dry for decades, and all of a sudden, I believe that was 2000. It's probably 2023. Water returned naturally, and I don't know if that's going to be. The water is going to be sustained, to be there, to be kept, or not, or right now is dried again. But that's something that happened in the past few years.
Yeah, thanks.
Yeah, I really looking forward to meet you in Namibia. As I said, my students literally work on that project. And apparently, for those individual lakes, you want to model, you want to simulate dust emission from this individual surface. What kind of emission scan that you're going to use, and how you are going to apply these emission scans. It's going to be challenging because there's no vegetation, or there's some kind of vegetation on the lake bed, and the soil is going to be different from your regular soil database. Okay, and it's going to be fun. I don't know how to do it exactly. We want to start with something that we know, something that is going to be relatively accessible, and then hopefully we can scale it up to something of global.
Okay, I worked only locally on lakes and paleo lakes in Mongolia and also in China, but mainly in Mongolia recently. Okay. Right. Let's chat. Let's discuss this in Namibia. Well,
I will do it. I'm looking forward to meeting you there.
Yeah. Okay. Thanks.
Thank you, Frank. I think we normally aim for 1 hour, so we're slightly over time already. And I see that people are disappearing from the crowd. So I would like to thank you again, Jimmy. Many thanks for your excellent talk, and congratulations once more on the mid-career award. And before we close the session, I would like to draw your attention to the upcoming last seminar in this series. It's given by Kat Fitzsimmons on the 3rd of June. Please have a look at the website, aeolianresearch.com. And as already announced by Frank and Jimmy, there's going to be heaps of discussions in the ISAR meeting in Namibia in July. And we all look forward to seeing you there. So thank you once more, Jimmy, and look forward to catching up either in June or in live in Namibia.
Thank you very much, JB. Really appreciate it. Yep. Well, see you there.
All right. Yes. Bye-bye.
All right. Bye.